let's just, what we're going to do is zero in on the most important aspects of statistics, and I hope I can do it in 3 hours. So what is it? What is a statistic? Can somebody answer for me? Don't worry about the notes too much. Just, what is a statistics? What's your understanding of statistics, or what is a statistic? Can you define it? Maybe you're going to Google it, but I want you to put it in your own words, because that reflects understanding. Well, statistics as a discipline is a branch of applied math, sure, but what is a statistic? Okay, Diego says it's like a summary of numbers. Okay, good. It's a summary of numbers. What kind of numbers? It's good though. So to understand what something is to discern what it is not. So numbers, what do you mean numbers? Okay, Tanya says statistics are a probability. Okay. I think I am going to say statistics are not. Yes, I guess it can be. It's a measure, a metric that could be a probability. You can interpret it as a probability, I guess. Yeah. So Xavier says a summary of data in numbers. Okay, so keep going. A few more guesses. I'm reading them out because I'm concerned we're going to lose the chat. Oh my goodness, I got the update. Let's see if this helps. Helps me connect. Okay, Diego, by numbers I refer to bigger amounts of numbers like data. Okay, so you guys are hovering around the point. You're very, very close. Statistics are calculated, or I'll say statistics are numbers calculated using data from the keyword is sample. So you had most of that, but just the sample part. So statistics are numbers calculated using data from a sample. Statistics are numbers calculated using data from a sample. So presumably the data from a sample also has to be numbers, right? The data, the values of the variable. Okay, so the keyword that was missing in your response was the sample. What's a sample? What's a sample? Right. So, okay, so a sample, a representative piece of the whole. Okay, a group taken from a population. Es una muestra, características en común tomadas de something. A random selection of the whole. Okay. Right. So samples are so we got to start first with the variable of interest. Okay, we begin with a variable of interest, a characteristic of interest. Okay, so given a variable of interest like the GPA of students in the fourth year finance program, let's say that's the variable of interest. Now, the population would be, for that variable, all students' GPAs. All fourth year students' GPAs. So a sample could just be the GPA of the students in my class. Is that a good sample? Is that a bad sample? Is it a representative sample? Those are different questions, but it's still a sample, right? It's just it's a portion of the population. So Paula mentioned random. That could be, that's not necessarily random, it's just everybody, right? So sample doesn't have to be random, it doesn't have to be good, it doesn't have to, it should be a good sample and it should be random. But a sample is just a sample. Could be bad. Could be good. So sample is simply a smaller or a portion of the population. It could be for people, it could be for interest rates, it could be for incomes of people, it could be for returns on stock. Okay, so a sample is a portion of the population, and what if the portion is 100%? What do we call that kind of a sample? We call that type of a sample a census. Okay, so most samples are just a portion, not 100% of the population. This is a smaller portion. So, back to, so a statistic is a number calculated for a sample that the sample is usually a fraction of the population of measures, right? Of numbers that are collected from the population. And it doesn't have to be, right, so statistics are good if the sample is good, if the sample is representative. Okay. So statistics, so what is the point of the statistic then? Why do we compute statistics? Excellent one. So we use statistics to predict what to expect. Expect from what? Or expect from who? From the population. Very good. Okay, so in particular, a statistic, okay, let me see. The goal of statistics, as I've defined it, and S1 reiterated, is to better understand what to expect, right? But specifically, a statistic is computed to estimate a parameter. What is a parameter? Nope. It's not exactly behavior, but what is a parameter? What is a parameter? In relation to what we've discussed so far, what is a parameter? Nobody has an idea. A parameter to predicted prediction. No. A parameter, okay, let's repeat. A statistic is a number computed from a sample. A parameter is a number computed from what? A population. Tanya is close there. A parameter is a number computed from a population. Okay, so the issue is we calculate statistics from a sample of the population as an estimate of the parameter in the population when we don't have all the population data. Okay, so a census is nice, where we have all of the data available to us, the whole population, and then we can calculate the parameters, which are really our goal. We want to know, what is the GPA of all students in the 4th year finance? If we have the information in our data, in our database, in our system, registration system, then we can just calculate it. But in place of that, if short of that, or we don't have access to that, we take a sample and we try and estimate for the population. Okay, so this terminology is really important. Sample are used to calculate statistics. And parameters from population or from populations. But the trick is, or the problem is, that we don't have all the population data. So the second best approach is to use a sample, a good sample that's representative of the population, to estimate what it is in the population. So that is the goal of statistics, okay? To compute good representatives or estimates of population parameters, to be able to do what? To be able to make predictions of what to expect, because there's so much uncertainty. How much I'm going to make this summer in my job? How much am I going to, what's the chance that I'm going to find a job when I graduate? What is the risk associated with taking on, an investment opportunity? So that's where we're headed with this. We're going to try and alleviate that uncertainty, and I just needed to clarify that terminology, that whether you had that or not. So just to go through what I'm saying here. So the goal of statistics is to gain information from data about a variable so that we can better understand what to expect and alleviate uncertainty, right? Uncertainty creates tension and stress, and there's lots of things we want to know about the future. And some people would like to know about the future because they can take calculated risks about decisions, that alternative decisions they can make. Okay, any characteristic of a person or thing that can be expressed as a number is called a variable, like dollar sales, quantity demanded, interest rates, etc. A value of a variable is the actual number that describes the person or the thing. The distribution of a variable tells you what values it takes and how often it takes these values. That's really important. Okay, so a distribution is going to tell you what values a variable takes and how often. So when you have data, that we'll presume it was a good data collection method that you used, or someone used and gave you this data, you want to be able to look at the data in a systematic way. And what you want to look at first is a graphical representation of the data. So you spend time in your statistics classes learning how to visualize data. And based on the visualization, this is really important. Based on the visualization of the data, you compute statistics, okay? You cannot just put numbers in a computer, ask for statistical data, which you can do in some software, and then present that as a report. You need to interpret what you get. The computer doesn't do that thinking process for you. The user has to do the thinking process. Which statistics do I use? Which ones don't I use? Often when you put data into using, I don't know if you learned how to use R, or you've learned just how to use Excel for statistics, or you've just done things with your calculator, which we will review. Some statistics are inappropriate. Some computations of data are inappropriate given the distribution of the data. Okay, so we're going to talk about that. So what do I say here? We can represent data by displaying characteristics of its distribution in two complementary ways: graphically and by statistical summary. It's important to explore both visually, graphically displaying the data, and then statistical summary when deciding how to report on a variable. Keep in mind that depending on the amount of data and the shape of the distribution, different statistics are used. So our goal then for graphical representation is to display a distribution to help best reveal its features, including regularities and curiosities, and then depending on the 5 features of the distribution, a different set of summary statistics should be reported. And then I just repeat what is a statistic and what is a parameter. And I repeat what I said here. Okay, so for instance, let me just check the chat if you have any comments. Okay, no comments. So what I've done here is I've said, okay, if we had the entire population, we could compute the population parameters for a variable. There are many different population parameters. When a distribution is symmetric, this is really important, it should be in bold, but when a distribution is symmetric, we refer to the mean and the standard deviation. And we use symbols like this symbol you've probably seen in statistics, right? That is a Greek letter for M. It's mu in Greek to stand for mean. And this symbol is sigma, which is Greek letter S, to stand for standard deviation. When you see Greek letters in statistics, what does it mean? Why don't they just put M? Why don't they just put S? What do the Greek letters imply? Tanya says parameters, which is the right answer, and Juan says Greek letters imply it's harder. Well, it's funny, but it kind of, yes, it's harder to get those values, right? Because if you don't have the population, you can't actually calculate a parameter. Okay, so don't be intimidated by the parameter. It's to convey to you that, yeah, it's a number that we might not have, but in theory, that's what we wish we had, okay? In principle, that's where we're headed. We want to have a number that represents that. So we have to give it a special symbol. It's pretty universal in statistical literature and any kind of science textbooks. The symbols are universally used or adopted. Different languages still use mu and sigma. So I've written here, these would be useful in describing the distribution if we knew the population had a symmetric distribution. So you should only use these for symmetric distributions. And we'll talk about symmetric distributions in a minute. However, it is usually not feasible or likely that we can attempt to measure the entire population. Sometimes you can. Sometimes you can. Like I can get the GPA of all the students in 4th year in our program. I can get that. But often it's not. So we use an estimate. So the symbol in the sample, so if we get a sample and we calculate the average, we use this symbol, X bar, to represent, let me make this a little bit bigger. I don't know. No, that's not making it bigger. What am I doing? All right. So we use this symbol, X with a bar on top, to represent the sample mean. Now, when we communicate about means and standard deviations, or any statistics, we often drop the prefix. So you often don't hear sample or population after the first class in statistics. You have to be clear about what you're working with. Okay, often you're working with, most of the time you're working with sample statistics, meant to estimate the population parameter. So that's the symbol for the mean of the sample. This is the symbol S, is the symbol for the standard deviation of the sample. Let me see if you guys can see that. Oh, it cut off. Let me get that on the screen. Sorry. No pretty way to deal with this. Okay, there you go. Okay, so you should have seen this. If you took statistics, you've seen these kinds of symbols. I'm just trying to make it second nature to you. Any questions so far? So somebody gives you data to analyze. Doesn't matter what it is. I'm going to end off with talking about financial data, but it could be anything. This is the thing I'm going to teach you, the systematic approach to reporting on a data set is pretty standard. What you want to be able to do is present the 5 features of the distribution. Remember, distribution gives you the values and how often they occur. The 5 features of the distribution will be reported to reveal regularities and curiosities in the data. You begin, and this is like an order here, you begin looking at a distribution by commenting on the shape. Either the shape is symmetric or the shape is not symmetric, or we call it skewed in English. How is that in Spanish? Same. So symmetric, what is symmetric and what is skew? Here we have a discussion about shapes. The middle distribution. Let's see, what is this hump? Where is this coming from? For people who are like, what is that? Okay, let me take a moment. I'm going to scroll down through here. Here's an example. This is an example of data from a marketing consultant has for a grocery store. This is a distribution representing the values of how much people spent at the grocery store and how often we see those values. And we want to use this data to answer 2 questions. How much did shoppers spend in the stores? You want to summarize how much they spent, and you want to recommend how this information can be used to improve the store's marketing strategy. So shopping data was taken, the grocery store spending data was taken and put into this graph. This is called a stem and leaf plot, and particularly it's a split stem and leaf plot. Because what we do is first we put the data in order. And can I write with this? That's not a, this was a pen. No, that's a signature. Sorry. Sorry, this is me and my new computer. I just realized I can't write on here. Tools. I'm being cheap and I don't want to pay for the I don't want to pay for the subscription because I have another computer with a Acrobat Pro on it. All right. So what we have here are the classes. I'm sorry if you hear the construction. Here are the classes or the bins for values. And the first one, I didn't want to do that, sorry. I don't know how to delete them. That didn't work. Sorry. Okay, so the first one is values $0 to $4, and the next one is $5 to $9, and the next one is $10 to $14, and the next one is $15 to $19. You see, so this is the stem, which is the first digit, and these are the leaves, which are the second digit. Now, I don't expect you to make anything like this in the class. I'm just showing you that there's a pattern here. That's really what I want to get out of this. There's a pattern. What shape is this distribution if I put this distribution on the horizontal axis? What shape is this distribution? Is it, which one of these is it, A, B, or C? Okay, sesgada. That's skewed. And it's A, right? It's going to be the A. It is. It's right. It's called right skewed. It's right skewed. Or sesgado a la derecha. So I say it's right skewed because there's a few observations that are high, but most of them are around the same value and much lower than those few high. Okay, so this represents the data for spending in the grocery store. What are some other examples of right skewed? Well, give me some variables that would be right skewed. Okay, if you have any questions about what I just did, calling it right skewed, let me know. So student motivation, okay, what would be your variable? So some measure of a motivation at the beginning of the school year. So what you're saying, Juan, is that most students will not be motivated and just a few will be highly motivated? Or are you getting it backwards? So your variable, the variable is on, along this axis from left to right, small to big. So often income is viewed as a right skewed variable. You often hear people talk about the 1%, right? The few billionaires in the world or in the United States. That would put them up, just a few up here where most people are down below. Okay, so income is right skewed. What's an example of left skewed? Can you give me an example of left skewed? So that's where just a few have low values and most people have a higher value of that variable. Or most people or most measures are measured high. Okay, so Juan, your example fits, Juan's example fits left skewed. Where he's saying at the beginning, most have high motivation and just a few do not. If you're thinking of the scale as time, that's a whole nother thing. If you're saying that, if you're talking about the variable being motivation throughout the college degree, I think that's what you're trying to say. And then throughout, on average, motivation is high and then it wanes towards the end. That would be right skewed. So anyway, I have to be clear about what it is your variable is. So my example that I put here about left skewed would be something like school grade completed. So let's say school grade in what do you call it, high school could be from, well, depending on the school. So we could say from grade 8 to grade 12. Let's say we made a histogram, we made a distribution of that. Most people have about grade 9, 10, right? At the age of 18 and over, most people have about grade 10, and then other people have graduated, like a lot of people have graduated, and there's a few people at age 18 who have no, very low or no grade school completed as far as grade 8 to 12. And that might be because they have some mental challenges or maybe they arrive as immigrants and they don't get the education. I'm just trying to think of extreme cases. So there's just a few, right, down here where by age 18, people don't have a grade 8 education, at least a grade 8 education. So anyway, so this is an example of left skewed. I'll give you an example of right skewed, and then there are the symmetric distribution. That's in the middle here. So the symmetric distributions, what are they? That's where most of the observations in the data set are around a certain value. Some are higher, and just as many are lower. Few are much higher, but just as many are much lower. It balances out around a predictable expected value in the middle. So if you have a symmetric distribution, using the mean is a good measure of expected value. The mean is here. But it also turns out that there are other measures of center that fall there. There's two other measures of center that we often talk about, and one is called the median and one is called the mode. In a symmetric distribution, they're all around the same class. They're in the same group. They all fall around the same place. So it really doesn't matter if I use mode, median, and mean to represent the expected value, but the convention is to use the mean. And there's a specific reason for that, and the development of statistics has been around using the mean for symmetric distributions. The development of statistic, good estimates, and then proofs that they're good have been developed using the mean. So we use the mean. So what should we use? So everybody got that? So in a symmetric distribution, repeating, in a symmetric distribution, the mode, median, and mean are all around the same thing. So what is the median and what is the mode? What's the difference? Okay, Ariana says that the mode is the number that repeats the most, or it's better to say modal class is the class that repeats the most. The class where the values fall, like the group, okay? Because it's not exactly the same. You can say the same value, but in terms of looking at these graphs, I'm talking about the classes. So what I've done is I've grouped numbers together as though they are similar. So I've said from 0 to 4, these numbers are kind of the same number, and I put them in a group. And then I put 5 to 9 in a group, and so those are classes that I group like numbers together so I can stare at the data. Otherwise, it's really hard to visualize what I'm looking at. Ariana continues that median is the number that's in the middle of the ordered data. Okay, so it's the middle value. Sometimes the median is not a data point, but it's an average of the two middle values. So, any questions about that? So let me review that here, and then I'm going to go back to the comparison. So what's the mean? The mean, this is really, 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 really important, okay? The mean is the expected value when you have symmetric data. It is known, well, it's the expected, we call it the expected value. But in cases where we don't have symmetric data, we prefer to use a different measure of center, and I'll explain why. The mean uses all of the values. What is the mean? It's the average, right? The mean is the average. You take all the values, you add them up and divide by the total number of values. So you use every single value in calculating the mean. The mean is the position in the distribution that sits closest to all of the points of the distribution, or all the points in the data set. It does so in a way that it balances the distribution, the weight of the values themselves and how many there are, against the other side, the weight of the values and how many there are. And you notice, to balance a skewed distribution, the mean is not at the mode. It's not at the most frequent observation. So the mode is always found where you have the peak, okay? The mean is pulled to balance off the distribution. So some of us, some people have no problem visualizing this, but just try to put your finger here and balance this distribution. It will not balance at the mode. It will tip over. And it won't balance too far out on the tail. It will tip over this way. So it's a very specific place where you find the center of gravity of the distribution, and that is going to be the mean. So you probably didn't know that when you just average numbers, you're just getting the average. But what you're finding is the balancing point of this distribution. The median is different because, okay, what's the difference between the mean and the median? The mean uses all the values in calculating. It's the sample average of the observation. So you use all of the values. Do you use all the values to calculate the median? So the question is, do I use all the values to calculate the median? I have to shrink my view again, don't I? Somebody answer my question. Do you use all the values of the sample to do you use all the values to calculate the median is what I want to say in general, whether it's a sample or a population. Well, so one is saying you need all the values because you have to put them in order. But do you use all the values to make a calculation to identify the median? Danella says no. Danella is correct. Okay, you don't use all the values. So for instance, let's say I gave you these numbers and I put them in order. So those are the numbers, those are the data. What is the median? So you have 1, 3, 5, and 7. What is the median? So one says the median is 4. So how did he calculate that? So he just took, well, anyway, it's in the middle. 4 is the average. You end up using the average of just 3 and 5. Exactly. So that's correct. So you only used those middle numbers to calculate the median. You didn't use all the numbers. Yes, you needed to use all the numbers to put them in order, but that's not what was used to compute the median. Okay, this is really important. As a result of only having to use the middle values, the median is not affected by the extreme values. It's not affected by those few observations in the tail. So it means that the median is not so sensitive to those extreme values, and it's a better representation when the data have extreme values. So it turns out that when data are skewed, so here A is the mode. Okay, so that's the mode. C, usually closer to the tail or extreme values than the other measure of center, which is the median. The median is the compromise. The median comes in between, always between the mean and the median. Sorry, the mode and the median. The median, between the mode and the mean, we find the median, and it's always the case, all right? When you have right skewed data and when you have left skewed data. But the order is different because the mean comes first, because the mean is closer to the few observations because it gets sensitized. It's affected because every single value is used in its calculation. The mode is over here, and that leaves the median in the middle, all right? So it turns out that when data are skewed, we prefer to use the median as a measure of expected value. In finance, we deal with stock return data a lot. And in this course, we pretty much focus exclusively, I can't think of anywhere that we don't, on symmetric distributions. Now, don't let that allow you to forget the difference between symmetric and skewed. All right, so that's why I take a moment to mention it here. So we are going to focus on symmetric distributions in finance, the mean as a measure of expected value, which shouldn't be very different from the median or the mode anyways, but that's how we do things, okay? We work with the mean. Now, mean is, symmetric distributions are a good representation of historical stock return data or stock market data, which is really important for us, and you'll see that. So don't forget that, okay? Also, symmetric distributions are assumed when for standardized testing, and they are the case for many things we see in proportion, human populations, and height and weight of adults. It's usually symmetric, where I explained most of the observations are in the middle. Some are higher, but just as many are lower. Some are much high, few are much higher, but just as many are much lower. It creates a mirroring effect through the mean. Let's see if you have any comments. You think so, Juan? Sounds similar. So, do I have the summary here of what I just said? Okay. Okay, so in this box I say report the mean as the center of symmetric data and the median as the center of skewed data. And then I mentioned something we'll talk about later, the geometric mean and holding period return. What you have here, and don't worry about this too much right now because we'll talk about it later. This should look familiar to you. Anyway, we'll talk about this later. I'll bring it up. I'll just leave it here as an example of another kind of mean, and I will go more deep into this later. I mean, next week. Okay. So, what I want to say, going from a set of data, this is just like a sample, right? Meant to represent the shoppers at the store. And I just take a few weeks of data, or a day of data, it doesn't say here, as a sample of the whole, and I make a graph, and then I smooth out the graph, right? I make it smooth. So I go from this and I make it smooth. What does the smoothing do? So what does this do? What are we saying when we do this? Like make a curve around it. So whenever you see a curve like this, you imagine underneath is like a stem and leaf plot or a histogram, like a bar chart, right? Something's under here, and then we smooth. What does it mean when we smooth? What is that all about? Is that intuitive for you, what we're saying when we do this? Yeah, same sort of logic one to determine what's best, better measures. So when I smooth out the distribution, understanding that there's a bar chart under there or a stem and leaf plot under there, when I smooth out, what I'm doing is I'm suggesting, or I'm making like an executive type decision that this, even though it's just a sample, represents the population. Okay, I'm saying I believe that the pattern will, if I had more data or all of the data of the population, I believe it will exhibit this pattern. So you can make decisions to smooth over any kind of bumps. So even though you'll see like some jagged type of shape, often people will just summarize with a smooth curve. Okay, and by doing so, they are, I'm going to make a note here, by smoothing, we are we're making like an idealized representation of the sample and suggesting that if we had more data or even all the data, we believe the pattern would look like that. So no real jaggedness, like nice and smooth. So I don't know if you know what I mean. If you make a histogram and it's kind of like going up and down and up and down, the bars are not smooth, we tend to just smooth over it and just say that's just an artifact of having a data set that's not complete. Okay? So we stick with the smoothed out version. That's what you often see. But you have to understand, under there is understood to be the data grouped into similar numbers in rank order. Okay, let's see how much I decided to show you here. So, all right, so let me go, sorry, I'm scrolling through, don't get dizzy, close your eyes. All right, so here are the 5 features, and I'm only gonna focus on the first 3, but for your sake, I'll mention the other 2 briefly. So we talked about, first you have to make a graph of your data, and you have to determine if it's symmetric and skewed, and I explained the difference. But I said to you, in finance, we pretty much work with symmetric data, but you need to know what to do with skewed data, so I mentioned some things. So with symmetric data, out of the 4 possible alternative measures for center, we focus on the mean in finance because the data that we work with are symmetric often, and we work with the geometric mean, so kinds of means, and I'll talk more about the geometric mean next week. The next feature of the distribution is the spread of the values, because just a single value, expected value, isn't really enough, right? An expected value doesn't tell you about how uncertain that expected value is. So we need a measure of the volatility or variability of the values, all the values together. And that measure for a symmetric distribution is called the standard deviation. If you don't have a symmetric distribution, you have to use percentiles, where the median is the 50th percentile. For the shape, you need to use other percentiles. The 5-number summary it shows the quartiles. So we're not going to get into that because in finance we don't use that. We focus on symmetric distributions and standard deviations. The other two things that you would mention when you're summarizing a data set is you should mention as a feature the gaps in the distribution and any outliers. Okay? In our case, it's not relevant because we're working with symmetric data, so there aren't gaps, but there could be outliers. You could have so what's an outlier? Outliers are values that are away from most of the data. So when data are skewed, often you test to see if the observations out here are so strange, we should call them outliers and investigate them. Have more to say about them. So you need to take some time to study those extreme values and decide if maybe there was an error in the data set or if they're legitimate values. And in a lot of cases, there's all kinds of cases. Sometimes they do represent a certain group, like over here, the 1% income earners who do exist, and they're very small group of people or households. But sometimes it could just be an error in the data, and you have to determine if it's an error, and you can dump it out, and maybe you end up with the symmetric distribution. All right, so it could be a symmetric distribution can also have outliers. Does anybody know what we consider an extreme value or an outlier for symmetric distributions? How do you tell if an observation is an outlier in a symmetric distribution? Okay, so Juan says something out of the bell. Okay. Do you know how far out of the bell? Or where does the bell end? Does the bell end? Does the bell go forever? What is an outlier in a symmetric distribution? Okay. The bell ends in the red line. Okay, we're going to talk about that. I really want to get my iPad working, but I can still talk about this without the iPad for a moment. I think I need to reboot my computer too. So let's take 5 minutes. I'll leave you with that question. We might be losing the chat because I keep on resetting my computer. So you might have to listen to this and take notes if you're not going to see it in the chat. But I'm going to reboot my computer and hopefully it'll sync with my iPad and I can do this properly. But the question I'll leave you with for 5 minutes is, what is an outlier in a symmetric distribution? How to identify if there are any outliers? Okay, I'm going to leave that with you. I'm going to reboot my computer and be back in 5 minutes, okay?